All right, this is Mr. Anderson for Kellogg Community College, and I'm going to be talking a little bit more about Chapter 3, Section 3 in the dreaded third part of our fourth-part series about Chapter 3, Section 3, solving trigonometric functions. And boy, we got a real doozy of a video ahead of you because we are going to be looking at changing omega from 1 to not 1. We're also looking at some phase shifting with our good old friend phi. And then we get into some factoring and substitution. So it's going to be a rough ride, and we're going to top it all off with the trigonometric identity. So get ready, folks. This is going to be a rocky ride. So what we're going to do first in problem number 16 is that, oh no, like in the previous video, we have a situation where theta is not all by itself. Here we have omega being 3, so we're speeding up this graph 3 times its normal speed, which means we're going to have more solutions than we're probably used to, but we're going to phase shift this graph a little bit to the left by 18th units. So let's see where we're going to be. To start off this work, we're going to write down 3 pi plus pi, or 3 theta plus pi over 18 is equal to where sine is equal to 1 on the unit circle. And sine is equal to 1 on the unit circle at luckily only one place, which is at pi over 2. Now this is going to repeat itself every 2k pi, and we have to write this down because in case of us changing the speed of the cycle, we are actually going to have more than just this one answer on the problem. So what we're going to do is get theta by itself. We're going to subtract pi over 18 from both sides. Now, to subtract fractions that have non-common denominators, we have to get one. So the common denominator between 2 and 18 is 18. So this would be 9/18 instead of just pi over 9/18 pi over 2 instead of just pi over 2. And now we'll subtract these two and get 8 pi over 18. But 8 pi over 18 is the same thing as saying 4 pi over 9 plus 2k pi is equal to now 3 theta. We're going to divide everything by 3, so everything gets divided by 3. I'll put a little division of 3 symbol there. So my theta is going to be equal to 4 pi over 9 divided by 3, which is the same thing as multiplying by a third. So I have 4 pi over 27. Then what I'm going to get is 2k pi over 3. So what I have to do, since I'm looking for my answers between 0 and 2 pi, not including 2 pi, I'm going to see how often 4k pi, or 4 pi over 27, which happens to be the first of possibly many solutions, when else is this going to happen? Since we sped up the sine wave 3 times as fast, we're going to have more than just this one situation occur. So now we have to take 4 pi over 27 and add 2k pi 3, or 2 pi thirds, over to see when this is true. And to get a common denominator between 3 and 27, that would be 27. And to do so, I'm going to multiply this 3 by 9, so now it's 27. I'm going to multiply this 2 by 9, so now it is 18. So 18/27 is the same thing as 2/3. It's equivalent. So if I add this together, I get another possible answer of 4 and 18, which gives me an answer of 22 over 27, which still is not yet to 2 pi, so I'm still within inside my first revolution of the circle. I'm going to add another 18 to my 22, and this takes me up to 40 pi over 27, which still keeps me within one revolution of the circle. But if I add another 14 or another 18, I'll get 58, and 58 is bigger than 2 pi because 54 over 27 would be 2 pi. So there is the end of my cycle right there. Now this next problem, number 17, is going to take a little bit of room, so I'm going to probably annex like a huge portion of this worksheet and then scroll it up when I'm ready to move on. So this is another problem where we're slowing down. See, my omega in this case is, that should look like an omega. My omega in this case is equal to 1/3. So what I'm going to do here is I'm going to write my equation as theta divided by 3 minus pi over 4 is equal to 1/2, but actually on the unit circle, that 1/2 is located in two places. It's located at pi thirds, and then that would repeat every 2k pi. And I have to include that because maybe by changing the speed, we're going to make this problem more or less frequent. And in fact, when I'm slowing this down, it's going to make it less frequent. But I also notice that when I'm looking for this answer of 1/2, it happens again for cosine, and it happens again for cosine at 5 pi over 3. All right, so I'm going to have my theta over 3, and this is going to be minus pi over 4, is equal to 5 pi over 3 plus 2k pi. I've got a hypothesis here that I'm not going to even use this, because once I slow this down, that's going to be much higher than 2 pi, but I'm still going to kind of work it out and show you that the left side is pretty much all we need to do here. So I'm going to add the pi over 4 to both sides. So pi over 4 to both sides to try to get my theta all by itself. And I'm going to go a third plus a fourth. I'm going to need common denominators. So the common denominator between a third and a fourth is 12. So this makes 4 twelfths, and this makes 3 twelfths, for an answer of 7 pi over 12. For adding, again, a third plus a fourth is 7 pi over 12, plus 2k pi. I'm now going to multiply everything by 3 to get rid of the 3 over here on the left-hand side. So that's going to get multiplied by 3. That gets multiplied by 3. So the 3's simplify. Theta is equal to 21 pi over 12, which I'm going to simplify, and this is 6k pi. Wow, 6k pi. That's pretty fascinating in terms of its spinning around the circle there. Again, it's going to take us a long time since the cycle is so slow. So theta is going to be equal to, simplify this, is going to be 7 pi over 4 plus 6k pi. I have one of my solutions, which is 7 pi over 4 right there, since that's between 0 and 2 pi. Now, if I go do the same things over here, watch to see what happens, because I'm going to take my theta divided by 3, and I'm going to add pi over 3 to both sides here. And in doing so, I get 5 pi over 3 plus 1 pi over 3 gives me 6 pi over 3. So that's 2 pi plus 2k pi. And then you'll see that once I multiply everything by 3, my theta is going to be equal to 6 pi plus 6k pi. I'm well past my boundary, so this is my only answer to the problem within one revolution of the unit circle. Obviously, I will have more answers, but I'm not looking for an infinite set of answers. I'm looking for the set of answers inside of one revolution around the unit circle. So my answer is 7 pi over 4. All right, so now let's work with some squares again, and we've worked with a problem like number 18, but problems 19, 20, and 21, oh my goodness, those are going to be some new stuff for us. So I'm going to do number 18 and 19 on this screen, and then I'll scroll down and do 20 and 21 for the end of this worksheet. So I'm going to add 1 to both sides to try to get theta all by itself. So sine squared theta is equal to 1. I'm going to then rewrite this as the sine of theta squared is equal to 1. I'm going to take the square root of both sides. This is important because a lot of people forget that when you take the square root of both sides, you have to take into account the positive or negative nature of the problem. So then we look at the unit circle at positive or negative 1 at the sine location. And again, I'm kind of skipping this step here where I'm looking at all instances when the inverse is going to be inverse of sine is 1 or the inverse of sine is negative 1. I'm kind of skipping writing this stuff down since I have a unit circle in front of me. I can see that sine, the theta is going to be this answer when sine of theta is equal to plus or minus 1 at the space of pi over 2 and 3 pi over 2. So now comes a little bit of a tough problem, because in problem number 19 you have a cosine squared and a cosine theta. And one of the real rules, or going back to Math 121, is that if you have a variable squared and a variable, you've got to factor it, because there's no way you can actually isolate cosine or theta on either one side or the other, because you have a power of 2 and a power of 1. So what we're going to do is we're going to let a variable u, this is a substitution step, let u equals cosine of theta. And that means that u squared is going to be cosine squared of theta. And in doing so, we can rewrite the problem as 2u squared plus u minus 1 equals 0. And that means we get to factor this. And this is a tricky trinomial, so for those of you who had me in Math 121, we'll see this pattern emerge. You're going to take your first term and multiply it by your last term, which is negative 2. List all the factors of negative 2. In this case, it's negative 1 and 2 and negative 2 and 1. And figure out which combination would make the 1u in the middle here. And the combination that makes that true is this first combo up there. So I'm going to split this up into negative 1u plus 2u. So I'm taking this combo and putting it here, because what's going to happen is I'm going to get a 4-term problem, and we're going to factor in terms of grouping. We take the first 2 terms, and we factor out a common term. In this case, it would be a u. So this is going to be 2u minus 1. And we're going to take our next 2 terms and factor out a common term, which is the only thing, which is 1. So this leaves me with 2u minus 1 equals 0. So now I have u plus 1 and 2u minus 1. This is the last step of grouping factoring, where we take the this term here that's doubled up, gets distributed by these 2 terms here. So this is our way we write the end of our grouping step. You kind of know you got it right if you have 2u minus 1 twice. So what we're going to do now is we're going to take these 2 parts, and we're going to substitute cosine back into u. So we have cosine plus 1 is equal to 0, and 2 cosine, I'm sorry, I forgot my thetas there. 2 cosine theta minus 1 equals 0 as well. So we have these 2 situations because these 2 equations are equal to 0. So either this is true or this is true, or they're both true. We just have to, look at our unit circle. So we'll subtract 1 from both sides, and we have cosine theta equals negative 1. So to define theta, we'd look on the unit circle where cosine is equal to negative 1. And here we're going to add 1 to both sides. So 2 cosine theta is equal to 1. Divide both sides by 2. Cosine of theta is equal to 1/2. So what I'm going to do is look on the unit circle when these situations are true. And we can see that in 3 spaces. The first space that we see is that at pi over 3, my cosine is equal to 1/2. At pi, my cosine is equal to negative 1. And then back again at positive 1/2, the the 5 pi over 3 is going to give me my other value where my cosine is equal to 1/2. So I have 3 solutions to this problem thanks to factoring. And for those of you who may not have remembered the tricky factoring, problem number 20 is going to help us, jar our memory again. So here we go, problem number 20. I'm going to pretty much monopolize the top half of this screen with this problem because it is another tricky trinomial. So let me at first partition this like so. Okay, so now what we will do is we will look at this problem, and since there's a cosine squared and a cosine, so since we're basically down to one trigonometric function, we're going to let u, we're going to let u equal to cosine theta, and therefore u squared is going to be equal to cosine squared theta. So this gives me the equation 2u squared minus 7u minus 4 equals 0. So again, with a tricky trinomial, we're going to go 2 times negative 4, which gives me negative 8. And we're going to list all the factors of negative 8. So 1 and 8, and negative 8 and 1, negative 2 and 4, negative 4 and 2. Sorry, those 4s look a little funky. So which combination makes a negative 7? And that combination right there is the second one on my list. So I'm going to split this up into 2u squared minus 8u minus 1u, I can put a 1 there if I'd like, minus 4 equals 0. So now I'm going to complete my factoring. I'm going to take my first 2 terms. I'm going to factor out a 2u. And if I factor out a 2u, I get an answer of u minus 4. Now over here, I'm going to factor out a negative 1 for my second 2 terms, which is going to give me a, let's see here. Oh, shoot, that should be a plus 1. That's where I made my mistake. So, but I'm going to factor out, in this case, a plus 1, haha, and that will give me a u minus 4 equals 0. All right, so that's how I could check as I was doing my factoring. I know I've done the grouping problem right because 2 of these will match, and I'll write them once. And then the other 2 pieces left behind, 2u plus 1 is equal to 0. Now I'm going to plug cosine into u. So now I have either the equation cosine theta minus 4 equals 0, and I have 2 cosine theta plus 1 equals 0. If I move the 4 to the other side, cosine theta equals 4. No, that's a extraneous solution. It isn't going to be part of our answer set. And over here, I'm going to have 2 cosine theta is equal to negative 1. Move that over there. I'm also going to then divide by 2, so cosine of theta equals negative 1/2. And if we look at our unit circle, we should have 2 instances of this. And the first instance of this is 2 pi over 3. And the second instance of this is 4 pi over 3. So there we go. There are our 2 answers. All right, now for our final problem today, and our final problem, it's a bit of a doozy because at this start of the problem, it has not only sine, but it also has cosine in it. So our first goal is to try to get this down to one kind of trigonometric function, because we can't solve a problem with both sine and cosine into it unless there's some serious simplification. So this is kind of unfortunate, but we do have to go back to one of our trigonometric identities that we threw at you in the first unit. And that trigonometric identity was based on the unit circle of x squared plus y squared equals 1. That's the definition of a circle. So therefore we could say that that the cosine squared x plus sine squared x is equal to 1. And now what we're going to do here is we're going to actually try to get rid of this cosine squared. So I'm going to subtract sine squared x from both sides. And what this is going to give me is cosine squared x is equal to 1 minus sine squared x. Now what's cool about this is, we see what I just circled right there? Since cosine squared x is equal to this, I'm going to plug that in for this up here, and this will get my entire equation down to one trigonometric function. So I'm going to have 1 minus sine squared theta minus sine squared theta plus sine of theta is equal to 0. Now what this is going to give me is, I'm going to do some simplifying of like terms here. I'm going to have 1 minus 2 sine squared theta plus sine theta equals 0. And when I have a sine squared and a sine, I am going to have to do substitution again. And I'm going to do substitution right now at this step here to make things a little easier to see. So I'm going to let u equals sine of theta. So this means I'm going to have 1 minus 2u squared plus u equals 0. And I'm going to do some factoring here. But I'm going to actually, having done factoring for a lot of years, I kind of know that if my first term, this u squared term, is negative, it's going to be kind of a pain. So I'm going to actually move everything over to the right-hand side, which will change everything from a positive to a negative. So this means this is going to be a positive 2u squared, this is going to be a negative u, and this is going to be a negative 1. So with that in mind, now what I will do is do some factoring. So in a tricky trinomial like this, I'm going to multiply 2 times negative 1, which gives me negative 2. Now I have to think of all the different ways I can break up negative 2. So 1 and negative 2, negative 1 and 2. Now, what combination makes a negative u? What combination makes that right here? Well, the combination that would make that would be this first one. So I'm going to split this up into plus u minus 2u, because that would give me a negative u, and I'm going to have the minus 1 and the 2u squared right there. So 0 is equal to this. Now what I'm going to do is do a little grouping. So I'm going to factor something out of here. I'm going to factor out a u, and that will give me a 2u plus 1. And then I'm going to factor out a negative 1 here, and this will give me 2u plus 1. So this is both equal to 0. So now I can write my factored final form of u minus 1 and then 2u plus 1. Now, then I'm going to, after I've completely factored this and set it equal to 0, I'm going to plug my sign back into this. So I'm going to kind of like go over here and rewrite it. So this is going to be 0 equals sine minus 1. Also, 0 equals 2 sine plus 1. So either sine of theta, oh, I forgot my theta is up there. Okay, sorry about that. There should be a theta by each of these. Sine of theta is equal to 1. Wait. Is that right? Yes. Sine of theta is equal to 1 because if I move the 1 over to the other side, it makes a positive 1. And on this case, I'm going to move the 1 to the other side. So negative, this is positive, so it's now negative 2 sine of theta. So sine of theta is equal to negative 1/2. So now I get to look at the unit circle. Woo! I get to look at the unit circle where sine is equal to 1. Or where sine is equal to negative 1/2. And I can see all of those, and gosh, I'm running out of room here, so what I'm going to do is change colors so you can see where I'm writing the answer in this field of math. And I am going to show you that negative 1/2 for sine is going to be the case at 7 pi over 6. If you look at your unit circle, 11 pi over 6 for positive. Now again, this is for sine equaling 1/2. And let me see here, 7 pi over 6. Let's see, negative 1/2. Yeah, okay, I'm just double checking my work here. And then 11 pi over 6. And then if I want to find it at exactly 1, that would be pi over 2. And I feel a little bad because I didn't write these in order. Pi over 2 would technically go first because that would be first on the unit circle as we were traveling, so you may want to reorder those. But as I told you folks, this is quite the page here, as we are going to now dig deeper in the final part of this video into some really good trigonometric manipulations here for this worksheet. So thank you for watching. I appreciate it.